its anti-particle, then the mass will be the same, the spin might be the same. I mean, there's only two possibilities. It'll be one of those. The thing that will be different is the charge. So that's kind of something that will distinguish or make you be able to, that's what makes the particle distinct from each other. And the particle's state, it's kind of like the quantum state of the particle is given by those things, the mass, the charge, the spin. In some cases, there is another property as well, depending on if it's a quark, right? So once again, just a quick recap. The particle family, there's three types of particles. There's leptons, quarks, and bosons. Once again, an example of a lepton is the electron or the muon or the tau or the neutrinos. Actually, there are three flavors of neutrinos that we have talked about as well. So that's in the lepton family, Lepton. Then there's the quark family of particles. Quarks are another whole type of particle, and examples of a quark would be the up quark or the down quark, things that make up stuff like our protons and neutrons within an atom. So subatomic particles, or really the nucleus of an atom, has more particles in it, protons, neutrons, which break down further into these things called quarks, which are in that family. Lastly, we have the boson family of particles. This includes things like the photon. The photon, which is of course light, is the particle nature of light, is a photon, is an example of a boson. All of these particles that I just now mentioned, so all of the above, when you write down the quantum state of a particle, you will have things like its mass, the charge, and the spin. And in the case of quarks, there's one more property. But hopefully that kind of makes it a little bit more clear what I meant. Basically, think of it as an identifier. If I tell you the mass, like say if you didn't know that it was an electron, but I told you its mass, its charge, its spin, then you could tell me that it's an electron. Okay, stuff like that. But the electron is a very common example. There could be other particles that are not as well known, or wasn't as well known, or wasn't discovered. And this is actually how many more types of particles were subsequently discovered. We kind of talked about that from that book that I was referencing yesterday, which is that there was a time in the 20th century, in the late 20th century, where pretty much almost every day we were discovering a new particle, or so it seemed, okay? And there's quite a bit of diversity and sort of variety and possibilities with these types of quantum states, like when you change the state and get a new value, say like you find, I'm just saying, you could think up a particle, right? You could think up a particle which has maybe the charge of an electron, the spin of an electron, but like a different mass, right? And in fact, that's actually how we discovered more types of leptons, right? It's like, oh, same charge options, same plus or minus charge, basically, either because, photons are neutral, like they don't have a charge. So like, what are the charge options? It can be positively charged, negatively charged, or neutral, right? So if I tell you this particle has a negative charge, it's not a photon, right? Like that's out, like it can't be a photon, right? So it's almost like playing, what's that game where you try to guess it? Something like dumb charades or 20 questions or something where basically, or what's the game where you basically try to say, oh, this, it's an actor. Yeah. Say it's an actor, but you try to say exactly like guess who type of thing, where you're like, okay, this actor was in the Titanic. This actor is female. This actor is very well liked in this live chat. So this actor played Rose. This actor must be then this actor drowned her boyfriend. So it is, what's her name? Kate Winslet, right? So that's how you know that Kate Winslet is Kate Winslet. Well, it's not Rose. She played Rose, right? So the same thing